In the 1920s, San Francisco was geographically trapped. Situated at the tip of a peninsula and frequently blanketed in heavy sea fog, the city had no direct overland route to the counties in the north. Reaching the rest of the state meant relying on a fleet of ferries. As the region grew, this transit system became completely overwhelmed, creating a physical bottleneck that threatened to choke the city's economic expansion. Building a permanent crossing across the Golden Gate Strait meant confronting a terrifying gauntlet of natural obstacles. The gap is a mile wide, with waters reaching 300 feet deep, all battered by hurricane-force winds. Below the surface, massive tidal shifts pull roughly 2.3 million cubic feet of ocean water through the narrow chasm every single second. To secure the city's future, engineers had to invent entirely new techniques to conquer an environment that actively resisted human intrusion. The financial hurdles were just as steep. The extreme tidal currents made this work incredibly dangerous. Divers were restricted to 20-minute windows between tidal shifts, feeling their way through pitch-black water to clear the blast debris. To block the currents, engineers constructed a colossal concrete ring called a fender. They then pumped 9 million gallons of seawater out of the center, creating a dry, watertight bathtub right on the ocean floor. By establishing this dry workspace, human engineering claimed its first major victory over the Pacific currents. With the foundation set, the towers began to rise. Millions of pounds of steel were manufactured in Pennsylvania and shipped through the Panama Canal to assemble the tallest bridge towers on Earth. These 746-foot structures were built using a cellular design, riveting together thousands of hollow, staggered steel boxes. This cellular structure provided the precise mechanical flexibility needed for the towers to yield to intense winds and snap back into position without breaking. Supporting the roadway required cables 3 feet thick, which are too heavy to manufacture off-site and transport as a single unit. Instead, the cables were constructed in mid-air. Motorized shuttles traveled across the strait for months, pulling individual pencil-thin steel wires from one shore to the other. This cross-section shows the final result. Each cable contains 27,572 wires. Spun end-to-end, this wire could circle the equator 3 times. Once in place, hydraulic machines applied 1,000 tons of force to crush them into a tightly packed mass. The entire weight of the bridge is supported by this web of delicate threads, meticulously woven together in the clouds. The suspended road deck is designed for movement. Specialized expansion joints allow the bridge to sway more than 27 feet horizontally and rise or fall 10 feet vertically, depending on the temperature and the wind. Building at these heights prompted revolutionary safety measures. Chief Engineer Joseph Strauss mandated the installation of a $130,000 safety net, which caught and saved the lives of 19 workers. Despite these measures, the environment still extracted a cost. Near the end of construction, a 5-ton scaffolding platform collapsed through the net, and 10 men lost their lives in the freezing water below. Defying the limits of geography required a heavy toll paid in both raw material and human life. The Golden Gate Bridge opened in May 1937, arriving ahead of schedule and under budget. The bridge's iconic color was actually an accident. The steel arrived coated in a red lead primer, and the Navy originally planned to paint the structure with black and yellow stripes for visibility. Architect Irving Morrow fought to keep the primer's hue, officially called International Orange, because it provided a perfect visual contrast against the blue water and the region's dense white fog. A project driven by cold mathematics and survival produced one of the world's most recognizable works of modern art. Modern San Francisco relies on the bridge as a heavy-duty thoroughfare, with more than 112,000 vehicles crossing the strait every day. Keeping this living structure alive requires constant engineering, from massive zipper trucks that actively shift the concrete median during rush hour to massive shock absorber retrofits designed to withstand a major earthquake. The bridge stands as proof that the limits of human imagination and collective effort are stronger than the limits of geography. If you liked this video, please subscribe and press the bell button.